in this topic, we're going to discuss accounting for variability. And for this, we're going to use the Indian cattle data again, and we're going to look into this a similar example to as we've been looking in our other two parts on variability in this kind of series of the last few topics. But as said, back in topic 1 is more information on this case study, alongside the data and a paper on it, which kind of give a lot more information about it, which might be very helpful for you. But as a brief overview, just to recap, is that this is a case study, which is a survey in Bengaluru, which is a major Indian city which has experienced fast urban growth. One aim of this case study is to investigate the effect of urbanization on dairy production. So we're going to use the variable average milk production per cow as an outcome variable when we're accounting for variability. And we want to find variables that account for the variability in this outcome. So what variables affect the average milk production per cow? For example, if the average milk production per cow had a large variability, that had a large range between min and max, do we find that those kind of higher values between on that milk production occur more in a rural area where cows might have more access to land or something compared to an urban area? I'm not sure, I'm just hypothesizing, but that's the kind of idea of what we're going to look into. So this is our distribution at the start. We're going to look at the distribution of this outcome variable, average milk production per cow. And if we look at just this variable, we can see that the average milk production per cow ranges from 0 to what looks to be around 25 liters, which is pretty high, I think. And we can see there's fairly a distribution where most cows are producing around about 5 liters. A lot of cows are producing between what looks to be between kind of 4 and 12 liters of milk. Now let's just have a quick step back. What do we mean by variability? Well, if there was no variability, then all of the cows would produce the same amount of milk. So it would just look like this. So say we had all 66 cows that we, oh, not 66 cows, but all 66, it's not 66, is it? I'm getting myself confused with the other case study, with the Omani case study, but sorry about that. But if we were to say all of our rows, which look to be about a bit over 60 here, which is why I was getting confused. But if we were to say all of our cows, or all of our kind of households, or all of our farmers, if all of our farmers found that their cows produced on average 10 liters per cow, then we would have just one straight line up at 10. As it is, we don't have one straight line up at 10. We have this huge variability between, again, around about 0 and 24, 25 liters. So some cows aren't producing any milk, and some cows are producing a lot of milk, and most cows are producing around about 4 to 12 liters of milk. But we can see that there's variability to account for, because we can see that we can see a range of data here. We can see that there's values dotted around. Now, some of this variability can be accounted for by other variables in the data set, such as urban area, such as whether they pasture or not, things like that, other variables that we have measured in the data set from the survey. But some of this variability can be accounted for by something, but it's not in the data set. Maybe the farmers weren't asked that question. Maybe when they ran the survey, actually one big thing influences milk production, but it wasn't asked about in the survey, so we don't have it there. Or maybe it's not even that it wasn't asked about in the survey, but it's something that we don't have information on for this data, such as, rainfall amount or sunshine hours and things like that, sunshine hours might affect how good the produce is that the cows, sunshine hours might affect the nutrients in the grass or in what the cows are eating. And that might then affect the cow's milk production, for example. But we don't have variables on that in the data, so we won't, at this stage anyway, be able to check that. So we've got variability that can be accounted for by other variables in the data set. We've got variability that cannot be accounted for by other variables in the data set. And then we have just random variability, just that complete randomness that some days, some cows just produce more and some cows produce less, and it's just sheer randomness. So we're going to focus on this first one. We're going to focus on the variability that can be accounted for by other variables in this data set. How are we going to do this? We use something called an analysis of variance table, or an ANOVA table. We can use this as a descriptive tool to see how much variability in the outcome the different variables account for. In an ANOVA, the overall variation in the outcome is split into two components. That kind of variation, which is due to a differences in means, or which is due to those kind of variables that is accountable, that is because of another variable, and residual variation, which is our like leftover variation, the variation that is not due to a difference in those means, or the variation that we have not yet accounted for. So let's look, for example, at the number of meals given to a cow. This is a numerical variable, but we're looking at the number of meals that the cow consumed in a day on average. And we're going to go through this table. But what I will say actually at this stage is that there's some good resources down in the resources section, which really dig into an ANOVA table on exploring it, on going through these different components with some interesting examples. And on top of that, in the quizzes, there's questions to help you fill it in, and on interpretation. We'll get to the interpretation in a bit, but really recommend and that going through those sort of resources are going to help you a lot more to understand it. But as an overview here, and as an introduction here, this will hopefully help as well. But of course, always getting to do your own quizzes and interactivity is going to always be a lot more beneficial. But to introduce this ANOVA, so here we have these on our left-hand side. We have N meals, we have residuals, and we have total. And so N meals is this variable that we're first looking at, because we're looking at the difference between the number of meals, how the number of meals a cow consumed in a day on average affected the outcome variable, the average milk production. So number of meals is going to be our first variable that we put in. And then our residuals, so our number of meals looks at that kind of variation between different levels. So between having no meals, 1 meal, and 2 meals, what is the variation between those kind of 3 different areas, or those 3 different levels? And then we have residuals, which is our kind of within error, our leftover, as I said before, or kind of within, so for those who are on 1 meal a day, that kind of variability within that group. So I was wrong at the start. At the start, I said number of meals is numerical. I was completely wrong. It's a factor variable. And our degrees of freedom here is the number of factor levels minus 1, which means that we have 2 factor levels for number of meals. And this is going to basically be, it will either be that the cows are given 1 meal a day or 2 meals a day, or it might be 2 meals a day versus 3 meals a day. I'm not sure, but we can tell that by the data. I'm pretty sure it'll be the difference between 1 meal a day and 2 meals a day. And so here we're looking at the difference, as we said here, between treatments. We're looking at the difference on this row here for those the difference in that kind of, or we're looking at that variability in the outcome. So the variability in the milk production per cow of cows who had 1 meal a day against cows that had 2 meals a day. And then our residuals is that kind of, okay, but within those who had 1 meal a day, we still have variability in there. Why is that? We can dig into that one. And then our total degrees of freedom. So here we have our degrees of freedom. Our total is 291. That's the total number of rows in our data, our number of farmers, or whatever our unit is, minus 1. We then have our sums of squares, and the additional resources really dig into this using graphs and a lot, some techniques which will hopefully really help in understanding. This is just our case study example where we're just trying to give a brief overview to introduce the topic. But we then have our sums of squares. We have our mean sums of squares, which is the difference between our sums of squares and our degree of freedom. So this is our kind of, for each degree of freedom, what's the mean squares? And then our F value, which is the difference between our mean squared for the number of meals, so this 12.050, and our mean squared errors, so our 0.519, and our F value is 23.208. Now, this F value is kind of very important here. This tells us how much variation is accounted for by N meals compared to the residuals. Topic 10 looks into interpreting this F value a lot more. But for now, this F value is much greater than 1, which means that this value, this mean squared for our number of meals is much higher than our mean squared residuals, which means that a lot of variation, or some variation, is accounted for by N meals compared to the residuals. As I said, that gets covered a lot more in the next topic. And we're now going to go back to these sums of squares, but again, these sums of squares are also in additional resources. I really recommend you having a look through them because they are dug into a lot more, with a lot more information given on them, with graphs to explain these kind of concepts. As I said, this is the case study example just to introduce the concepts. But we can use this sums of squares to answer the question, how much variability in our outcome variable, so how much variability in the average milk production per cow is accounted for by the number of meals the cow has a day. And in our data, we can find that by dividing our sums of squares for our number of meals by the total sums of squares. And we see overall roughly 7.5%, 7.4% of variability in the outcome is accounted for by the number of meals. This is pretty low, but okay, we've accounted for 7.4% of variation in the outcome. We have not accounted for the remaining 92.6% of variation. This might be variability due to a natural error, that kind of those natural differences that occur, or it might be due to so that kind of natural variability, sorry, or it might be due to variables that we've not accounted for in our ANOVA. Now, this kind of 92.6% is a very high amount of kind of unaccounted for variability. But fortunately for us, we've got a lot of variables, and so we can add another variable to our ANOVA to account for more variability and hence try and reduce this. And so now we've added in milking technique, and this indicates whether milking was by hand or by machine. And if we do this kind of 12.1 plus the 3.1, we get 15.2. 15.2 divided by our total sums of squares are 162.6. Means that together, both variables now account for 9.3% of variability in the outcome. So 9.3% of variability in the average milk production per cow. And we can keep adding. We then add in transect, which we see accounts for quite a bit, and we add in settlement, which has less. or less than transect, but more than milking technique. When we've added in these 4 variables, we now have 24.7% of variability in the outcome. I mean, actually, maybe we'll leave the next bit up to you, maybe up to you. Try and get this number as high as you can. How close to 100% can you get? You won't get 100%, but how close, how much variability in the outcome can you account for? At the moment, our other 75.3% is the unaccounted for variability. This is split into kind of random natural variability and our unidentified variability. Unidentified variability is variability that can be accounted for, but it has not been. This might not have been accounted for because we've just not put those variables in the ANOVA yet, or it might be unaccounted for because we don't have those variables in the data set to begin with. So it might be as we said at the start, it might be that these are variables such as you know, more on the diet that the cow eats, and we just don't have those. We haven't measured that. We haven't asked the farmers that question, so we don't have that information. Or sunshine hours. We don't have that information in our data set, so it's not accounted for here. But actually, if we had that information, it would account for some of the variability in the outcome of that average milk production. The aim is to reduce the unidentified variability. The aim for statisticians, the aim for people using the data is to reduce this amount of unidentified variability, to increase the amount that we've accounted for, to get this value, or to get these values large, and to get this residual sum squared as small as we can. That's the aim. So we can continue to add variables to reduce the unidentified variability, but we won't here. But you can feel free to have a go at that and to see how close to 100% can you get. There's a lot more questions in the quizzes section, which are also on interpreting. So we really recommend you give them a go to really help in your understanding and to look at the other slides under resources on this. But overall, we've got these 4 variables and they account for nearly 25% of variation in the average milking amount. There's still a lot more to be accounted for in the data, and this can be found by continuing to add more variables to see the impact. The aim is to reduce that unidentified variability. Thank you.